Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
In very large-scale integration design, parasitic refer to unintended and unavoidable electrical elements that arise from the physical properties of materials, geometrical layout and device structures used in semiconductor fabrication. Although they are not deliberately designed into the circuit, parasitic significantly affect the performance, speed, power consumption and signal integrity of integrated circuits. As device dimensions continue to shrink into the nanometer scale, the impact of these parasitic effects becomes more pronounced, often dominating the ideal circuit behavior. In this video, we will explore the factors that contribute and impact the performance of a VLSI chip. So, let's get started. VLSI design process defines the system specifications, performance parameters and goals of power, area, etc. The RTL design using HDL implements the logic and simulation verifies its functionality. Logic synthesis converts a gate-level netlist and ports the design to the appended standard cell library. Floor planning sets block locations, power grids, and I/O pin positions. Placement arranges standard cells and macros within the layout. Routing connects all nets, vias, metal layers and ensures timing and DRC compliance. At advanced nodes, interconnect parasitic dominate delay and must be modeled accurately. Parasitic extraction captures parasitic elements of capacitance, resistance, and inductance of the layout design. The extracted parasitic data is superimposed on the design and carryout, static timing analysis, power estimation, IR drop evaluation, etc. Various steps shown in the flow diagram ensures that the fabricated chip realizes the desired functionality. Parasitic are an inevitable part of VLSI design and play a crucial role in determining circuit performance. It begins with material properties, which define the fundamental parasitic resistance, capacitance, and inductance. These inherent characteristics form the base of all subsequent interactions. As we move to the structural layout stage, design choices like routing, device placement, and interconnect proximity can amplify these parasitic through coupling effects and other proximity-driven interactions. At the gate level, these parasitic manifest as slower switching speeds and increased leakage currents, directly impacting power efficiency and speed. When observed at the functional level, they can cause timing failures, signal noise, and long-term reliability issues, threatening the overall integrity of the chip. Furthermore, second-order nanoscale phenomena, such as fringing fields, electromigration, and self-heating, introduce even more complex challenges as technology scales down. To address these issues, careful design practices, judicious material selection, and optimized layout strategies are essential for delivering high-performance, reliable modern VLSI circuits. Modern VLSI chips are built layer by layer, where each stage influences the design performance. Semiconductor materials, like high-purity doped silicon, define transistor speed, leakage, and reliability. Passive devices, parasitic like irritants, and stray inductance degrade the signal speed and power efficiency. Active devices are fabricated from overlapping layers of different material. Structural imperfections create parasitic capacitances that limit the performance parameters. Interconnects of copper and dielectrics form signal and power paths, create RC delay, crosstalk, and power integrity issues. Physical placement and routing determine the chip density, but closely packed wires increase parasitic coupling and delay. Chip packaging and assembly provides electrical connection and cooling but add to parasitic resistance, inductance, and thermal stress. At nanoscale, second-order effects like process variation, temperature rise, and substrate noise reduce yield and reliability. A holistic approach, from materials to packaging, is essential for high-performance and robust VLSI designs. In practical VLSI circuits, no component is truly ideal. Every resistor, capacitor, and inductor is associated with parasitic that becomes significant at high frequencies or in fast switching operations. These parasitic can impact the circuit performance, causing signal distortion, power loss, and timing issues, etc. For a resistor, the primary parasitic include Cp, a small capacitance formed between the resistor body and the substrate or ground. Lp, a small inductance in series with the resistor, especially due to leads or layout. Rc, small contact resistance at the terminals, representing imperfect connections. For a capacitor, common parasitic are ESR, the equivalent series resistance, a small resistor in series, causing energy dissipation. ESL, the equivalent series inductance, a small inductor, due to interconnect. Cp, a stray capacitance between plates and nearby nodes or the substrate. Rleak, a leakage resistor in parallel, representing non-ideal insulation of the dielectric. For an inductor, the parasitic include Rs, a small resistance in series with the coil, representing conductor losses. Cint, a small capacitance between adjacent loops of the coil. C-self, a capacitance from the coil body to ground. M, the mutual coupling from nearby inductors, that cause signal interference. These parasitic cannot be eliminated completely, but can be minimized and achieve optimum performance. Every integrated circuit begins with the silicon substrate, which forms the foundation for all semiconductor devices. Substrate's key parameters such as crystal purity, crystal orientation, carrier mobility, resistivity, and thermal conductivity directly impact speed, power efficiency, and reliability. Chip fabrication uses dielectric materials like silicon dioxide and silicon nitride in device fabrication, interconnect isolation and passivation layer formation. MOSFET, the fundamental building block, is made of sandwiched layers of semiconductor materials. Its key parameters such as threshold voltage, on resistance, and drain current define how it behaves electrically and dictate the circuit speed and power consumption. The device interconnects and power nets are created using aluminum metal. However, copper, due to its lower resistivity, has replaced aluminum. The proximity of interconnects create inductive coupling that leads to magnetic interference, resulting in ringing, electromagnetic interference, and power noise, which can affect the performance. Thus, careful material selection, structural design, and routing strategies are essential to ensure high performance and reliable chip. Let's review the MOSFET transistor capacitances. The thin gate oxide layer forms the primary gate capacitance. But parasitic capacitances also emerge between gate, source, drain, and body terminals. The gate has both channel coupling and overlap capacitance. The CGD and CGS are gate overlap capacitances. CGD provides negative feedback and, due to the Miller effect, increases input capacitances by GM times. Drain and source to body capacitances, CDB and CSB, are created due to reverse bias junctions. In normal application, as sources return to body, the CSB is ignored. Several physical factors contribute to these capacitances. Thinner oxide increases gate capacitance. Gate overlap adds to the parasitic load. Fringing fields at gate edges become dominant. Scale technologies. Wider device geometry adds to the parasitic capacitance. Physical design layers specified in the layer panel can be classified as base layers that are used to create devices. The interconnect layers are used to establish connectivity of signal and power nets, design rules, and that helps improving the manufacturing yield. Nanotech employs about 15 interconnect layers, which are routed at different vertical levels. They are of varying widths and are used for signal, power, clock nets routing. Metals routed at levels are isolated by oxide layers that result in creation of net parasitic capacitances. Parasitic created between the same level nets is called intra-layer capacitance, and between different level layers is called interlayer capacitance. As shown in figure, the physical dimensions of spacing, width and height determines the capacitance magnitude. These parasitic affect the performance parameters of the delay, crosstalk, noise, dynamic power dissipation, EM, joules heating, etc. After net routing, parasitic extracted are superimposed on the gate level design and timing performance is evaluated. With shrinking of technology, due to reduction of interlayer spacing, increases the parasitic capacitances. Characterized logic gates are provided by timing libraries. In VLSI design, the physical layout structure and geometry impacts the parasitic elements. Some of the issues are discussed below. Narrow and long interconnects. As technology shrinks, thinner and narrower metal lines exhibit high resistance, RC delay and IR drop, resulting in slower signal propagation and timing closure problems. Closely spaced nets. Dense routing increases the adjacent net's coupling capacitance and impacts crosstalk noise, glitches, dynamic power dissipation and false switching, etc. Stacked interconnect layers. In order to optimize die area, the interconnects are routed in multiple vertical layers. The stacked layers create interlayer capacitance that also adds the load capacitance. The cross-layer coupling leads to signal integrity issues and dynamic power consumption. Vias and contacts. The stacked metal layers and device pins are connected through contacts and vias. Via being a small cross-sectional area element, exhibits high resistance. As the technology shrinks, via resistance further increases, that lead to increased IR drop and temperature rise, that can lead to electromigration failure. Power and ground loops. Poorly designed power distribution networks create loops and uneven current paths. This results in increased IR drop, ground and supply bounce, and create an unstable power supply that impacts noise margin. This is critical for high-speed circuits and global clocks nets. Well substrate interference. As analog and digital circuits are mounted on a common substrate, the switching current IR drop and the substrate resistance creates interference. Thus created noise is coupled to the sensitive analog circuits that will experience performance degradation. CMOS logic gate performance is heavily influenced by parasitic effects of the device. Miller capacitance, the coupling between gate and drain, slows switching by increasing effective input capacitance, leading to higher propagation delay and power consumption. From the polysilicon gate and contact interfaces, limits current drive and cause slower rise and fall times in high-speed circuits. Substrate coupling occurs when switching noise propagates through the silicon substrate, creating crosstalk between adjacent devices and degrading signal integrity. Body-to-source and body-to-drain leakage currents caused by reverse bias junctions contribute to static power dissipation and can create incorrect logic levels in low-power designs. Together, these parasitic factors increase delay, noise, and power consumption, requiring careful layout optimization, shielding, and device sizing to maintain reliable CMOS logic performance. Physical layout design has direct impact on circuit performance, as it defines the placement and routing of devices that adds unavoidable parasitic. The parasitic of material properties, device structure, and proximity effects can lead to multiple performance challenges. Signal delay occurs due to increased resistance and capacitance of interconnects that slows down the signal transitions and degrades timing closure. Power consumption is increased due to parasitic capacitances that are to be additionally charged and discharged, resulting in additional power loss. The leakage current's unintended paths adds to static power loss. Noise and crosstalk, resulting from capacitive and inductive coupling between closely spaced wires by which active signals get disturbed with nearby lines and cause false triggering. IR drop, arising due to current flowing through resistive power rails, lower effective supply voltage and device operation. Poor layout can create parasitic switch paths, increasing latch-up risk, which can lead to chip catastrophic failure. These combined effects lead to signal integrity issues such as edge distortion, reflections, and high speeds ringing. Careful layout techniques like shielding, proper spacing, and optimized routing are essential to reduce layout parasitic. In VLSI physical design, parasitic introduced by device geometry, interconnect structures, and material properties significantly impact chip performance and reliability. Fringe fields occur due to electric fields spreading at interconnect edges, increasing unwanted capacitance and causing signal delay and power loss. Substrate coupling occurs when noise signals travel through the common silicon substrate, leading to interference between analog, digital, and RF blocks. Electromagnetic coupling arises from high-frequency currents in adjacent interconnects, inducing unwanted voltages and degrading signal integrity. Electromigration is a reliability issue where high current densities move metal atoms in interconnects, causing open or short circuits over time. Hot carrier injection occurs when high-energy carriers get trapped in the gate oxide, shifting threshold voltage and degrading MOSFET performance. Self-heating results from localized power dissipation, raising device temperature, which accelerates aging and increases leakage currents. These parasitic effects become severe in nanoscale nodes where wires are densely packed and devices operate at higher speeds. Careful layout techniques, such as shielding, isolation structures, guard rings, and controlled routing, are essential to minimize these issues. In VLSI design, RLC parasitic significantly impacts circuit speed, power, and reliability. Propagation delay occurs due to RC loading in long interconnects, slowing signal transitions and degrading timing closure. Crosstalk is caused by capacitive and inductive coupling between closely routed wires, leading to false switching and logic errors. Ringing results from inductive effects in high-speed signals, creating overshoot and undershoot that distort waveforms. Noise margin reduction happens when parasitic coupling and IR drop lower the effective signal levels, increasing vulnerability to the logic failures. Their performance impact includes timing violations, higher power consumption, degraded signal integrity, and reduced circuit lifetime. Prevention techniques include using shielding and proper spacing, controlled impedance routing, and increasing power rails width. The parasitic such as resistance or LC are introduced into a layout. They are to be extracted to form a circuit model that enables timing analysis. There are two popular extraction models used in VLSI design, namely Elmore and asymptotic parasitic extraction model. Elmore model focuses primarily on parasitic resistance and capacitance and ignores inductance. It is intended for moderate speed, RC-dominated interconnects only. As shown in the figure, the Elmore extracts tree-like RC network, meaning there are no feedback loops or complex coupling. The delay is calculated using the following simple principle. For every resistor in the path, multiply its resistance by the total capacitance connected downstream of it. Add up these products for the entire network to get the overall delay. That is, in an Elmore delay model, the delay is proportional to weighted sum of all node capacitances, where the weight is the resistance along the path between the source and that node. The advantages of Elmore model are, it is a simple and fast computating model that works well for a tree-like RC structures. Very good for early timing estimation and routing algorithms. The disadvantages are, it does not account for coupling capacitance or inductance. It cannot handle complex meshes or feedback loops. Asymptotic waveform evaluation model is a higher-order and more accurate delay model designed to handle complex RLC networks, especially in high-speed designs. AWE requires extracts, resistance, capacitance, and inductance along with coupling effects between wires. It models interconnect coupling, mutual inductance, and distributed effects that Elmore cannot capture. The AWE parasitic extraction process involves various steps like layout analysis, parasitic estimation, frequency response modeling, moment matching, and simulation integration. In simple words, the AWE parasitic extraction process takes a complex chip layout, converts it into a detailed RLC network, simplifies it mathematically using moment matching, and then predicts the actual signal waveform. The characteristic features of AWE are: it is highly accurate, suitable for deep submicron and nanometer nodes with high-speed signals. Computationally intensive and needs more simulation time and resources. Captures effects like ringing, crosstalk, and signal integrity issues caused by inductive coupling. Technology nodes ranging from 90 to 65 nanometers, 45 to 28 nanometers, 14 to 7 nanometers, and below 5 nanometers represent key milestones in the evolution of semiconductor fabrication. Each range marks a transition point, wherein the behavior of devices and interconnects changes dramatically, leading to new parasitic effects that dominate chip performance, power, and reliability. 90 to 65 nanometers node is the beginning of deep submicron era, wherein parasitic could no longer be ignored. Due to packed and closer wires together, the capacitance effects have dominated, resulted in introduction of low-K dielectrics materials and better routing methods. 45 to 28 nanometers node increased resistance and RC delays era. As wires became thinner and narrower, their resistance increased sharply, RC, the main performance limiter. In this era, increased leakage current led to higher power dissipation, along with increased IR drop and RC delay and worsening of crosstalk. 4 to 7 nanometers node high-speed operation and inductive effects era. At these advanced nodes, switching speeds became so high that inductive effects could no longer be ignored. Key challenges at these nodes are ringing and reflections caused by parasitic inductance, global interconnects, and clock networks. Also led to increased EMI and self-heating phenomenon. Below 5 nanometers node, extreme parasitic interaction era. At this node, all parasitic effects are L and C of string impact, and device scaling alone is no longer enough to improve performance. At this node, the key challenges are IR drop, EMI, SI, mutual coupling, noise margin reduction, etc. The above data highlights that parasitic management is important as transistor scaling and dictates the future of semiconductor design. Thanks for your time. Hope this video has been helpful in appreciating the origins of parasitic and their impact in VLSI design and performance. Thanking you once again. Hope to meet you in upcoming video. Bye for now.